Hey everyone, welcome to this video. Today we're diving into something that's fundamental to becoming a better Python developer: design patterns. Have you ever wondered if there's a right way to solve certain problems in your code? Well, that's where design patterns come in. Think of them as tried and tested solutions to common problems you encounter when writing software. Imagine you're assembling furniture from IKEA. Instead of figuring out how every screw fits, you get an instruction manual that shows you the best way to do it. Design patterns are like that instruction manual for your code. They save you time and help you avoid mistakes. Part 1: Introduction to Design Patterns. Definition: design patterns are essentially like a toolkit of proven solutions that help us tackle recurring problems in software design. Rather than reinventing the wheel each time you face a challenge, design patterns offer reusable and reliable solutions that have already been tested. These patterns follow best practices and provide a structured approach to building systems that are flexible, can scale easily, and are easier to maintain as they grow. They help guide us in making better design choices so that our systems remain robust and adaptable over time, no matter how complex they become. The key idea behind design patterns is that they offer reusable solutions to common coding challenges, helping you solve problems efficiently. When you follow a design pattern, you're ensuring that your code remains scalable, maintainable, and consistent as it grows and evolves. It's important to note that design patterns aren't just about writing code, they're more about shaping the overall design and structure of your solution. They guide how you build your system, making it easier to adapt to changes and maintain over time. By focusing on structure, design patterns help create software that can stand the test of time. Part 2: What is design patterns? Explanation: design patterns are like best practices for solving recurring problems in software development. They provide well established ways to structure your code, making it efficient, usable, and easy to maintain. Instead of coming up with a new solution every time you face a problem, design patterns give you a blueprint that has been tested and refined over time. You can then adapt that blueprint to your specific situation, saving time and reducing errors. Key concepts: 1. Reusable solutions. One of the key benefits of design patterns is that they offer reusable solutions to problems that developers often encounter. You don't have to reinvent the wheel every time. Instead, you can rely on these patterns to handle common tasks like object creation or component communication. For example, patterns like singleton, factory, and observer are widely used to manage how objects are created or interact in a system, providing a consistent and reliable approach across different projects. 2. Scalability and maintainability. Design patterns also help build systems that are scalable and easy to maintain. As your project grows in size and complexity, the structure provided by design patterns ensure code remains clean and organized. This makes it easier to extend the system without breaking anything. Take the adapter pattern, for example. It allows different components to work together seamlessly, making it easier to integrate new features or systems without having to rewrite large portions of your code. 3. Simple visual example. Imagine you are working on a program that needs a single database connection shared across different parts of the application. Instead of creating a new connection each time, you can use the singleton pattern. This pattern ensures that every time a request is made for a database connection, the same instance is returned, avoiding unnecessary duplication and ensuring that resources are efficiently managed. The singleton pattern is a practical example of how design patterns help you solve real-world coding problems efficiently. In this example, we are implementing the singleton pattern in Python. The singleton pattern ensures that a class has only one instance throughout the lifetime of the program, and that all requests for that instance return the same object. This is useful when you want to manage resources like database connections, logging systems, or configurations in a centralized way. The class singleton has a class level attribute underscore instance that is initially set to none. This attribute will eventually hold the single instance of the class. The core of the pattern is implemented in the underscore underscore new method, which is responsible for creating a new instance of the class. In Python, underscore underscore new is the method that creates a new instance of a class, while underscore underscore init initializes it. Here we override underscore underscore new to control the instantiation process. Inside underscore underscore new, we check if underscore instance is null. If it is, it means no instance of the class has been created yet. So we use super singletons dot underscore underscore new class to create one. This ensures that only one instance is created. If an instance already exists, it simply returns the same instance by skipping the creation step. When we create two objects S1 and S2, both refer to the same instance of the class. The line prints once S2 checks if S1 and S2 are the same object and it returns true, demonstrating that both variables point to the same singleton instance. Part 3, why are design patterns important in Python? Before diving into why design patterns are important in Python, it's worth noting that these patterns serve as foundational tools for developers. They aren't strict rules or predefined code snippets, but rather flexible guidelines that help address common challenges in software design. Whether you're working on a small project or collaborating on a large codebase, design patterns help streamline the development process, improve code quality, and foster better teamwork. Now, let's explore the specific ways design patterns make a significant impact on coding in Python. Cleaner code design patterns provide a structured approach to coding, helping you write clear and organized code. They allow you to follow a standard format, making your code easier to read and maintain, which is especially useful in large projects. Avoid common mistakes by using well-established design patterns. You can suggest common errors that many developers encounter. These patterns are the result of years of experience in solving recurring problems, so they guide you toward best practices and proven solutions. Reusable solutions design patterns offer reusable approaches to solving coding problems. Once you've implemented a pattern, you can apply it across different parts of your project or even in future projects, saving time and effort while ensuring consistency. Collaboration: when everyone on your team follows the same design patterns, it becomes much easier for team members to understand and contribute to the codebase. Patterns provide a common language that improves collaboration and helps in maintaining the project over time, even as the team grows or changes. Part 3, types of design patterns. Design patterns can be grouped into three main categories, each addressing specific challenges in software design: creational, structural, and behavioral patterns. These categories offer tailored solutions based on how objects are created, organized, and how they interact with one another in a system. By understanding and applying these patterns, developers can build flexible, scalable, and maintainable systems that adapt to changing requirements. Let's dive into each category and explore the key concepts and examples. 1. Creational patterns. Creational patterns are specifically concerned with the process of object creation. Rather than directly instantiating objects, creational patterns provide a flexible approach to handling object creation based on various scenarios. These patterns ensure that the right objects are created in the correct manner, making the system more adaptable and reusable. The main goal of creational patterns is to control how objects are instantiated without tightly coupling the code to specific classes, allowing for greater flexibility as the system evolves. These patterns simplify the process of object creation and make it easier to manage instances across large systems. Examples of creational patterns include the single pattern, which ensures that only one instance of a class exists, helping to use resources more efficiently and consistently. Another example is the factory pattern, which allows a class to delegate the responsibility of object instantiation to subclasses, providing a way to create objects based on input conditions without needing to specify the exact class of the object being created. These patterns enhance system design by streamlining object creation, offering more control and flexibility as requirements change. 2. Structural patterns. Structural patterns focus on how classes and objects are composed to form larger, more complex structures. These patterns ensure that even when one part of the system changes, the overall structure remains stable and manageable. They enable different components to work together seamlessly, promoting both reusability and flexibility. The primary goal of structural patterns is to organize and compose objects and classes in a way that forms larger, scalable structures without compromising the system's flexibility. By simplifying relationships between objects, structural patterns make it easier to extend or modify systems without requiring major rework. For instance, the adapter pattern acts as a bridge between incompatible interfaces, allowing systems to work together even if they weren't originally designed to be compatible. Similarly, the decorator pattern allows developers to dynamically add new functionality to an object without altering its original structure, providing a flexible way to extend behavior. These patterns are essential for maintaining modular, scalable, and adaptable systems as they evolve. 3. Behavioral patterns. Behavioral patterns are primarily concerned with how objects communicate and interact with each other to achieve specific behaviors. These patterns define the rules of interaction between objects, promoting loose coupling between components, which makes the system more scalable and adaptable to changes in requirements. By managing how objects collaborate, behavioral patterns ensure that the system functions as expected while maintaining the flexibility needed to accommodate future modifications. The key focus of behavioral patterns is on the interactions and communication between objects, ensuring that they can work together efficiently in a loosely coupled manner. For example, the observer pattern allows one object to notify others of changes in its state, making it ideal for event-driven systems like graphical user interfaces, GUIs, or messaging platforms. Another example is the strategy pattern, which enables the selection of different algorithms at runtime, providing flexibility in how tasks are performed based on specific needs. These patterns help build adaptable and scalable systems by defining clear communication structures between components. In summary, creational patterns focus on the process of object creation, offering more flexibility by controlling how objects are instantiated. With examples such as the singleton and factory patterns. Structural patterns, on the other hand, address how classes and objects are composed, ensuring the system remains modular and easy to model, as seen in patterns like adapter and decorator. Lastly, behavioral patterns concentrate on object interaction, ensuring efficient communication and collaboration between components, exemplified by patterns such as observer and strategy. Together, these patterns help developers build flexible, scalable, and maintainable systems. Part 4, Common Terminology in Design Patterns. In design patterns, there are a few key terms you need to know. A pattern is a reusable solution to common software problems, offering a template to solve challenges efficiently. Abstraction hides complex details while exposing only the necessary features, simplifying how we interact with objects. Encapsulation bundles data and methods in a class, protecting an object's internal state from outside interference. Polymorphism allows different objects to be treated through a common interface, enabling flexible behavior. Finally, loose coupling Vs. Tight coupling describes the degree of dependence between components, with loose coupling providing more flexibility and easier maintenance. Understanding these terms is essential for working with design patterns effectively. 1. Pattern. A pattern is essentially a reusable solution to a common problem in software design. Instead of having to figure out how to solve the same problem repeatedly, design patterns offer a best practice template that you can apply in different situations. Think of it as a blueprint that can be adapted to tackle various challenges across projects or pros. For example, the singleton pattern ensures that only one instance of a class is created during the lifetime of an application. This is particularly useful when managing resources like database connections or logging services, where having multiple instances could lead to inefficiency or errors. By applying design patterns, developers can work more efficiently, solving problems in a structured and consistent way. 2. Abstraction. Abstraction is the idea of simplifying a system by hiding its complex internal workings while exposing only the essential functionalities needed for interaction. This means you can use an object without having to understand all the technical details of how it operates behind the scenes. The key benefit of abstraction is that it reduces complexity, allowing you to focus on what an object does rather than how it accomplishes it. A great example of this is the factory pattern, where the client interacts with the general factory interface to create objects. The client doesn't need to worry about the specific classes or the instantiation process. Everything is handled behind the scenes. This not only makes the system easier to use but also more flexible and maintainable. 3. Encapsulation. Encapsulation refers to the practice of combining data attributes and methods functions that manipulate that data into a single unit, typically a class. This concept not only organizes code but also restricts access to certain components, effectively protecting an object's internal state. By limiting how external parts of the code interact with an object, encapsulation ensures that changes to the internal state are controlled and managed through specific methods, making the system easier to maintain and update. A great example of encapsulation can be seen in the decorator pattern, where additional functionality is added to an object by wrapping it with another object. This process allows new features to be introduced without altering the original object's implementation, keeping its internal logic intact while extending its behavior. 4. Polymorphism. Polymorphism is the ability of objects to take on many forms, allowing different objects to be treated as instances of the same class through a common interface. This concept is central to design patterns as it enables flexibility in how objects are used and interacted with. By allowing various objects to behave differently based on the context, polymorphism promotes cleaner, more adaptable code. For example, in the strategy pattern, different algorithms or strategies implement the same interface. This allows the client to dynamically switch between these strategies without altering the client code. Polymorphism simplifies the interaction between objects and increases the system's flexibility, making it easier to adapt to new requirements or changes. 5. Loose coupling Z's, tight coupling. Loose coupling refers to a design approach where components within a system are minimally dependent on one another. This design choice makes the system more flexible and easier to maintain, as changes to one component have little to no impact on others. The key advantage of loose coupling is that it promotes modularity, allowing individual components to be modified, replaced, or extended independently without causing a ripple effect throughout the system. A great example of loose coupling can be seen in the observer pattern, where observers are loosely connected to the subject. The subject doesn't need to know the specific types or details of the observers, making it easier to extend or modify the system without breaking existing functionality. This approach ensures scalability and adaptability, especially in larger, more complex systems. Tight coupling occurs when components in a system are highly dependent on each other, which makes the system harder to modify or maintain. In tightly coupled designs, changes made to one component often necessitate changes in other dependent components, leading to increased complexity. The key drawback of tight coupling is that it makes the system rigid and less flexible, as any adjustments in one part of the system directly impact others, reducing the system's adaptability. For example, in a tightly coupled system, if the subject and observer are closely bound, any changes made to the subject might require direct modifications to the observers as well. This results in a more complex and less flexible architecture, making future updates or extensions more challenging. Summary of common terminology. A pattern is a reusable solution to common software design problems, offering a structured approach to recoding challenges. Abstraction hides complex details and exposes only essential functionalities, simplifying how we interact with objects. Encapsulation bundles data and methods together, protecting the internal state of objects to maintain integrity. Polymorphism allows different objects to be used interchangeably through a common interface, promoting flexibility. Lastly, loose couplings is tight coupling compares design approaches. Loose coupling promotes flexibility and modularity, while tight coupling increases dependency, making systems more rigid and harder to maintain. Conclusion and key takeaways. Design patterns serve as blueprints for solving common coding problems, offering tried and tested solutions that help streamline software development. They promote writing code that is maintainable, scalable, and reusable, ensuring that projects can grow and evolve without becoming unmanageable. There are three main types of design patterns: creational, structural, and behavioral, each addressing different aspects of software design. By incorporating these patterns, developers can create systems that are easier to understand, maintain, and modify, making collaboration on large code bases smoother and more efficient. That's it for today's introduction to design patterns. If you're interested in diving deeper into specific patterns, stay tuned for upcoming videos where we'll break down the most commonly used patterns in Python with easy to follow examples. Don't forget to like, subscribe, and hit the notification bell so you don't miss out. Thanks for watching and happy coding.